Let's talk about the properties of gases. Gases have no definite shape or volume. That means they have a variable shape and a variable volume. Gases are fluids. A fluid is any substance that can flow, and gas particles flow because they are relatively far apart. So here you can watch, they can flow and be poured. Here with the sulfur hexafluoride, it is more dense than air, so when it is poured into that aluminum foil boat, the boat sinks. In fact, speaking about density, gases have low density, so they are relatively far apart, so most of the volume with a gas is empty space, whereas in a solid, the particles are tightly packed. So remember, density is how much stuff there is in a certain volume. And with a gas, typically there are less particles. And also, that means gases are highly compressible. So since the particles are far apart, we can squish them closer together. It's why you can get an oxygen tank that has far more oxygen in it, because you can squish those oxygen particles closer together. Gases will completely fill a container. So you can see in this GIF here, when the container is open, the gases spread out and fill the container. Why? Because the gas particles are constantly moving at high speed, so they will fill their container. Gas pressure. Gas pressure, remember, is caused by collisions of gas particles with the wall of the container. And this is partially due then to the fact that gas particles have mass. So when they bump into the container, it creates pressure. Now let's talk the kinetic molecular theory. The kinetic molecular theory is used as a model to predict gas behavior. It is based on ideal gases. Now, in reality, there are no ideal gases, but we're going to make this assumption that the gas we're talking about is an ideal gas so we can do calculations. So let's talk about the important parts of the KMT, or kinetic molecular theory. You have to know these. So first, gas particles are in motion. What kind of motion? Constant, never stopping. Rapid, moving fast. Random, so they don't have a planned out route. And straight line, so not curved. So constant, rapid, random, straight line. Constant, rapid, random, straight line. Gas particles are very far apart relative to their size. So this explains fluidity and also compressibility. In fact, we say that the volume of the particles themselves is negligible. That's how far apart they are. Gas pressure, remember, results from those particles colliding with the walls of the container. In the kinetic molecular theory, all collisions are elastic. That means the energy is completely transferred. The total amount of energy remains constant. So that means this particle hits this one and all of the energy moves to the second particle. That's not in reality how it happens, because some energy might be transformed into thermal or light or sound, but according to the kinetic molecular theory, all of the energy gets transferred. Gas particles have no mass or volume. So remember, this is the ideal. It doesn't really exist because gas particles obviously have some mass. Even the smallest, like hydrogen and helium, they do have mass. So we're talking about the ideal. And in order to do some calculations based on ideal gases, we're going to assume the particles have no mass or no volume. So the word that you'll see for that is the volume is negligible, meaning so small we're not counting it. And gas particles have no intermolecular forces between them. Now remember, this is the ideal because in reality there are going to be some intermolecular forces, but we're making an assumption in the kinetic molecular theory that there are none, okay? So when would gases be most ideal? So I know that there are no gases that are ideal, but when could they be most ideal? Like when would they fit those requirements the best, okay? In one situation, The gas particles that have the least mass will behave most like ideal gases. So these particles are smaller and have less mass, so they will be more ideal. When else? Well, when I'm looking at gas molecules that are non-polar, because non-polar molecules have the weakest intermolecular forces. So if a molecule is non-polar, it is more ideal than polar. Remember, polar, they have partial positive and partial negative, so there's stronger attractions. When else? When the pressure is low. Okay, so that means I haven't squished them real close. I've given them lots of space. That also means big volume. Okay, so I want to give those particles a lot of space. And finally, real gases behave most like ideal gases at high temperature. Why? Because remember, one of the requirements was moving quickly, and particles at high temperature are moving faster. So at high temperature, at low pressure means big volume also. And with low intermolecular forces, so that means nonpolar, and with small mass, that means particles like hydrogen and helium, okay? Those would be most ideal. All right, let's talk about heat flow. So remember, temperature is a measure of average kinetic energy. So when particles are moving slower, the temperature is lower. But what is heat? Heat is a form of energy that flows between two samples of matter that are touching because of their differences in temperature. Okay? And then there is an exchange of thermal energy due to the temperature difference. So heat is movement. It's moving energy. It's moving because of differences in temperature. So thermal energy flows. That's heat. And why is it flowing? Because of differences in temperature. How will it flow? It will flow from warmer to colder always. Warmer to colder. So heat will flow between objects when the temperatures are not the same, and it will flow until the temperatures are the same, and will always flow again warmer to colder. So warmer to colder until the temperatures are the same. So this one was warmer. The heat will flow between them once they are touching, and then the heat flow will stop when the temperatures are the same. So do not say that heat flows up or down or left or right. It's from warmer to colder. So in this case, it would flow from block A to block B. Okay, why is that true? Because I could put block B on top and then heat would flow up. But what if I put block B on the bottom? Then heat would flow down. So we don't really judge heat in terms of up and down and left and right. We say heat always flows from warmer to colder. All right, let's talk about Avogadro's law. Before we get into Avogadro's law specifically, let's review a couple things. First, what is a mole? It's a counting unit. It means the amount of a substance, and 1 mole of anything contains 6.02 times 10 to the 23rd particles. A mole of oxygen, 6.02 times 10 to the 23rd particles. A mole of carbon, 6.02 times 10 to the 23rd particles. And what is volume? Well, volume is the amount of space occupied by an object. Okay, so 1 mole of any gas, doesn't matter, hydrogen, helium, oxygen, fluorine, whatever. 1 mole of any gas at STP, standard temperature and pressure, look at table A, so you know what that is, occupies a specific space, that's 22.4 liters. Here's a little Taylor Swift reminder. 0.4. Okay, so 22.4 liters is the amount of volume in any gas that is at STP. So you can see here we are at standard pressure, standard temperature, occupies this space. Standard pressure, standard temperature occupies this space. Standard temperature, standard pressure occupies this space. They all have the same number of particles. They all have the same number of moles. What is the only thing that's different? The mass, because that is relative to their atomic mass. Okay? Point 4. All right. At STP, 1 mole of a gas occupies 0.4, 22.4. So what is Avogadro's law? Well, Avogadro's law says that equal volumes of gases contain equal numbers of molecules if they are at the same temperature and pressure. So that means at the same temperature and pressure, if they have the same volume, all of these have the same number of molecules. So what do I mean? Here's an example. What balloon would have the same number of particles as 3 liters of nitrogen gas? Well, if it's the same volume, it has the same number of particles. So which one has the same volume? Yeah, this one. Okay, so we're going to set up a demonstration. Okay, so this is our setup. We have a tub of ice water. We have a hot plate that is turned on. There's an empty can that was filled with about 10 milliliters of water, and it is set on the hot plate to begin to allow that water to boil and turn to water vapor or steam inside of this can. Now let's talk about gas pressure. So remember gas pressure, we've gone over this already. It's caused by collisions of gas particles with the walls of the container. How do we measure pressure? With newtons, with pascals, with atmospheres, with torr, with millimeters of mercury, and psi. This is mostly in tires. What do we use in chemistry? Typically millimeters of mercury, atmospheres, and Pascal, but we typically use kilopascals, so kPa. All right, air pressure is atmospheric pressure, and it's caused by the weight of a column of air pushing down on an area. Typically, we use atmospheres. Now, we don't typically notice air pressure. We're not like, oh my gosh, the pressure of the air on me is too much. But sometimes we do notice it, like when our ears pop when we're traveling in hilly areas or in airplanes. And that's because the atmosphere is denser closer to the surface, so our ears pop when the air inside matches the pressure of the outside. So when the pressure of the outside air changes as we're going through hills or mountains or in an airplane, the inside has to kind of calibrate to that. All right, now it's time for our demonstration. All right, so we have, you can see the steam coming out the top of the can, so that means this can is filled with water vapor. We have this container of ice water prepared, so I'm going to lift the can off of here and set it in the ice water. All right, so think about it. Why did that happen? What happened to the water in the can as it was heated? Well, it started to evaporate, right? Become steam, water vapor. And then what happened to the steam in the can when it was placed in the ice water? Well, it condensed, right? It became a liquid again. And as it did, the pressure in the can dropped. But the atmospheric pressure, the air pressure didn't change. So all of a sudden, the air pressure was able to squash the can. All right, so here you can see this on a much wider scale. So if you clean the inside with steam and seal it up, as the steam condenses, the air pressure drops, the atmospheric pressure stays the same. It can crush the gas tanker just like it did the can. All right, what is vapor? Well, vapor is a gas phase. What is vapor pressure? Well, that's the force exerted on the walls of a container when we have a closed container and it has some liquid. So there would be some of the liquid that's a vapor, and that vapor creates pressure, okay? As we increase the temperature, the vapor pressure increases. So the same substance at 50 degrees Celsius has a much lower vapor pressure than it does at 150. So you increase the temperature, it makes sense. More of the particles would be vapor, more particles would be hitting the walls of the container, higher vapor pressure. So we have a reference table that shows us vapor pressure of 4 specific liquids. So if they ask about vapor pressure, go to this table, okay? So it specifically asks about propanone, ethanol, water, and ethanoic acid. Now, boiling point is the temperature when vapor pressure and atmospheric pressure are equal. How will I know it's boiling? You'll see bubbles. So there's evaporation that can happen at any temperature, but when it's boiling, vapor pressure equals atmospheric pressure, and we see bubbles forming and rising. So on table H, where do we find normal boiling point? Well, it's that dotted line, okay? So what is the normal boiling point? Again, it's the temperature that a liquid boils at standard pressure. So this whole dotted line indicates standard pressure. They even wrote it here so we would remember. So what's the normal boiling point of water? Well, you go across that dotted line till you hit the line for water and go down, and what do you see? Yeah, 100 degrees Celsius. Now, remember, stronger intermolecular forces means a higher boiling point and a higher melting point. So on table H, which compound would have the strongest intermolecular forces at 50 kPa? So what I'm going to do is go across 50. Which one has the highest boiling point? That would have the strongest intermolecular forces. Okay, so that would be ethanoic acid. Which one would have the lowest intermolecular forces at the same pressure? Well, it would be propanone. Okay. All right, so at which temperature is the vapor pressure of ethanol equal to 80 kPa? Well, I'm going to go across from 50, 60, 70, 80 kPa until I hit the line for ethanol, okay, and go down and read the temperature, and that is about 73 degrees Celsius. Okay, whew, that was a lot about gases.